Hello students, let's continue to talk about the neuron and neuron physiology. In this segment we're going to be talking about graded potentials. So we're changing our focus now. We're changing what we're talking about. Up to this point we've been talking about the action potential. And that action potential, that's that long distance signal, it's the electrical impulse traveling down the axon of the neuron. In this case we're now talking about graded potentials. And these are small changes in voltage that occur in the dendrites in the cell body of the neuron, and they will ultimately may or may not lead to an action potential depending upon whether they're excitatory or inhibitory. So graded potentials, these are the small changes in voltage that are created in the dendrites in the cell body of the neuron when the neurotransmitters bind to their neurotransmitter receptors. And we have two types of graded potentials. We have EPSPs, which are excitatory postsynaptic potentials, and IPSPs, which are inhibitory postsynaptic potentials. If we continue to take a look at them, here's the action potential. And the action potential is this electrical impulse that's going to travel down the axon. Here are the graded potentials. And the graded potentials just occur within the dendrites in the cell body. They're short distance, they're small changes in voltage, and depending upon the graded potentials that I get, they could lead to the neuron firing, to the neuron creating an actual action potential. Once again, let's take a look at these graded potentials. In this case, a graded potential is caused by, it's also caused by sodium-potassium channels, but in this case, what is stimulating the opening and closing on the sodium-potassium channels are neurotransmitter receptors and neurotransmitters. And so when a neurotransmitter binds to a neurotransmitter receptor, this can open sodium and potassium channels and then change the voltage in that local area. In this case, here we have an EPSP, where we have an excitatory neurotransmitter. It's bound to a neurotransmitter receptor, and it's caused an EPSP. It's caused a slight increase in the voltage of the neuron. Here, this one is, in this case, it's an inhibitory neurotransmitter, and that inhibitory neurotransmitter has caused an IPSP. It's lowered the voltage and taken the voltage away from threshold. So that what happens then, basically, again, is that in terms of the EPSPs, I have a neurotransmitter, it binds to a neurotransmitter receptor, and it opens up channels in which the influx of sodium is greater than the potassium efflux, and that creates an EPSP. And if I have enough EPSPs, if I have enough neurotransmitters binding and they create enough EPSPs, that will cause the neuron to fire. That will cause the neuron to create an action potential. I'll reach threshold and I'll get the action potential. However, I can go and we see it right here. Here in this case I have a neurotransmitter binding, and the neurotransmitter opens up sodium-potassium gates. Enough sodium rushes in where I get an EPSP. I get a small voltage that's bringing the neuron closer to threshold. The opposite side of that is an inhibitory synapse, or inhibitory neurotransmitters, or IPSPs. In this case, I have an inhibitory neurotransmitter. It's opening channels for potassium and chlorine, and this is causing a hyperpolarization. It's causing the membrane of that neuron to become more negative, and it moves the neuron away from threshold. So in this case, I have an inhibitory neurotransmitter. The inhibitory neurotransmitter has bound. It's opened up potassium and chloride channels, and that has caused an IPSP. It's caused the voltage to lower. It's caused the voltage to go away from threshold, and that ultimately will make it less likely for the neuron to fire, and so it has an inhibitory effect. Thank you.